Okay, so today I will talk about engineering dwarfs at galaxy formation's edge. It's a collaboration among several different groups, in fact. So I'm... Sorry, what? Ah, sorry, okay, let me adjust this. What about now? Yeah. Okay, so engineering dwarfs at the galaxy formation's edge. I'm Oscar Agertz, working at Lund University. Lund is a small town in downtown Sweden at the very south. And this is a collaboration with Andrew Ponson at UCL, Justin Reed, University of Surrey, Martin Ray at UCL. He's joining us in Lund in a few months. Matt Orkney, a student at Surrey. Our friends Joki Roosdahl at University of Lyon, and the Zurich friends are over here, Romantici, Robert Rebecki, Michael Kretschmer, and Sarah Nickerson. So I'm showing you here a bunch of explosions to wake you up. It's the morning of the last day. And the point of this collaboration is to understand galaxy formation at the very edge, the smallest galaxies, ultra-faint dwarf galaxies. We have a logo up here, so we saw some nice logos this week. And this one is designed by by Matt Orkney at Surrey. I also made a logo that was voted down by the collaboration. Looks like this. So I may use it in the future, but for now, let's stick with the other one, okay? Okay. So the census of dwarf galaxies, there's been an explosion in the last decade and a half. So digital surveys have really revolutionized this. This one is a plot taken from Josh Simon's review of this year on the faintest dwarf galaxies. So here we see year and number of confirmed and the candidate Milky Way dwarf galaxies. So around the advent of SDSS and DES have really changed our picture of what the smallest galaxies are. Okay, so now we have almost 60 confirmed and candidate galaxies around the Milky Way. This is where they sit in the sort of magnitude size relation. Okay. So up here we have globular clusters. These diagonal lines show the surface brightness, lines of constant surface brightness, and we are sort of inching our way down to more extended diffuse things, and we have the latest ones that we have discovered are very small in size and indeed very faint. Okay? And many of these also have a spectroscopic follow-up, so we have much more information about these. And it's fascinating, so we don't know where this will end, okay? So this is roughly our current limitation with current technology. And in the future, we hope we will find even more objects lying down here. Yeah, so we maybe still been missing a diffuse ultra-faint population. And these discoveries have also started to indicate that the globular clusters and ultra-faint dwarfs are sort of bleeding together a little bit. So there's a lot of interesting overlap here to be understood. Okay, so what do we like to understand? Okay, in this project, and I think in general about ultra-faints. So what is the edge of galaxy formation? What is the smallest mass halo that contains a galaxy, and how do they form? How do stellar masses relate to halo masses at the dark matter halo masses below 10 to 10? Scattering, stochasticity, and occupation fractions. What do we expect here? I will also refer you to Fra Munchi's talk later this session. She will give an overview on this, I believe. Origins of the currently star-forming ultra-faints, such as Leo T. So there are these very faint objects lying just outside the real radius of the Milky Way. They have H1 forming stars, and it's a puzzle how they could have survived the reionization. Structural diversity at the edge. What is driving this? What's the physics behind this? Do we expect dark matter cusps or cores in these systems? And then what my talk will be mostly about now, role of star formation and feedback physics on these scales versus environment and assembly history. And there's been a slew of work on this, obviously. So here are some of the recent literature on this. So I would say it's a fairly hot topic to understand this. See also the poster by Anna Wright and Elad Applebaum as well. Okay, stellar mass-halo mass relation at the edge. Okay, so the first thing to realize is that there's no clear theoretical consensus below 10 to 10 solar masses. So here I'm plotting in lines here are the extrapolated abundance matching relations. In blue here we have from Justin Reed, You get a similar one from Peter Brutz's extrapolation, and the black one is a popular one from Ben Moster. And here are some simulation efforts, some recent ones here. Okay? And there's quite a bit of scatter, as you can see here. Okay? It turns out that individual efforts tend to produce fairly well-defined relations. So, for example, this is now just a rough line I'm drawing here. This is what we get in many of the simulations adopting the fire feedback physics. These ones here are from the work of Farah Munshi and her collaborators. And all the work by Justin Reed and myself, we found, in non-cosmological ones, found a much more efficient galaxy formation scenario. So it's quite a spread here, right? And at least 2 decks in terms of what we find between different modeling groups. So this is a bit of a hindrance because we want to actually quantify the expected physical scatter in order to interpret upcoming, forthcoming servers like LSST. Okay, so this project then, what we're going to do, I'm going to show you the first steps of this project. And so we're doing galaxy formation in 10 to 9 or to 10 to 10 solar mass dark matter halos. We're doing a range of assembly environments, as well as engineered histories. So we'll get back to in 6 or 7 minutes. So where we can do a bit more robust experiments within a cosmological framework. We're using the cosmological radiation hydrodynamics code, Ramses RT, as well as Ramses, to do this. We're reaching fairly good resolution, 20 solar masses in gas resolution, 3 parsec spatial resolution. We explored non-equilibrium cooling, multi-frequency radiative transfer, several photon groups, coupling between this and molecular hydrogen formation, radiation pressure, etc. And a slew of different feedback physics, supernovae, stellar winds, AGB, mass loss, etc. Okay. And the first step then, before we embark on a big campaign, is to then understand what is the role of this physics that we put in. ISM, star formation, and feedback physics. So this is, so we pick one halo, 10 to 9 solar masses, and we run this in a variety of different ways. So here is what it looks like in temperature. Okay? So it's again very explosive. So the main galaxy, main progenitor is seen here. And this thing is quenching at around redshift 4. And in the simulations, the majority of the supernova cooling radii are resolved by more than 6 cells. So good. So it means that hopefully the momentum is captured at least from these explosions, and even the hot gas phase, we believe. And this is, of course, a pain also for the time step, of course, because the blast wave velocities can be 5 to 10,000 kilometers per second in this case, right? So you can have really diffuse explosions. And you can see how violent it is if you zoom in here a little bit, right? So we're getting coupling on extremely large scales as well as small scales, depending on where we are during the starbursting. Okay. Okay, so yeah, just to quickly recap of what we're trying to do. We want to understand the impact of radiative transfer on these ultra-faint dwarfs, understanding the role of molecular hydrogen physics and star formation, especially what happens if we couple radiative transfer to the abundance of locally on molecular hydrogen. So these things are very metal poor and very dust poor. And a bottleneck ought to be the formation of molecular hydrogen out of which stars form, and also then how it's destroyed by Lyman-Werner radiation from young star-forming regions. Strength of supernova feedback is something we want to understand, and especially to see how we can match up with other groups. So we artificially boost this up to 100 times the canonical values and also weaken it. We try different UV backgrounds to see if that changes the formation history. And of course also numerical resolution to see if we can get some convergence. So I won't show you all of this. I will show you like a little a teaser of our key findings. The first thing is radiative transfer. So this is now on-the-fly radiative transfer, and it really changes the mode of dwarf galaxy formation completely. Okay, so here we have different temperature projections at different redshifts. So this is without radiative transfer or radiative feedback, and with. Okay? What we find is that once you have radiative feedback, you calm down galaxy formation at this mass. Not too strange maybe, because the virial temperature of these objects is always below 10,000 Kelvin. So you expect radiative, even local radiative or UV radiation to have a big impact. And this makes it less violent. So the supernova scenario is extremely explosive. This is not really the case here. It's much less vigorous in terms of its outflow properties. We can see it in gas density. This is just to visually illustrate this. There's more gas hanging around the galaxy. So it's warmed up, likely, we think. And it's kept in that phase instead of being blown out to insane distances. So what happens? I already alluded to this. This is now a PDF. Okay, so a mass-weighted temperature PDF. Okay, so this is where the mass in the galaxy is, basically. So I stack these between redshift 4 and 13. Okay, so without feedback, most of the gas, before ionization especially, enters quite cold. And when you form stars, it's in very cold, dense clumps, okay, even in these dwarf galaxies. If you then add in your supernova feedback, so you get this crazy evolution you've seen in the movies, it doesn't change this picture very much. Okay, it lowers the total mass, and maybe it doesn't get to the extreme high densities we get without feedback. Boosting this by a factor of 10 doesn't do very much to this evolution. Okay? It lowers the star formation rate somewhat in a sublinear way. And when you turn on the radiative feedback, it changes the picture completely. Okay? So you're dominated by warm gas everywhere in the ISM and just outside. And this is what sort of limits the star formation in this case. So you don't need to blow it out. You can just keep it in a reservoir or non-star forming gas. We still have bursty star formation always. Okay? So it's not like we're changing that aspect of this. So this is now star formation rate. This is now look-back time. So with and without this radiative feedback, we will still have bursts of star formation. It's just that these are less violent, and coming from both the local heating of the gas, but also the fact that you're cooling down in a much slower pace. Okay. So that's what's happening here. Okay, the stellar mass halo mass relation. Let's get back to this. So what happens now in our models? This is now the extrapolations I showed you before. These data points here are so this is now empirical, or this is derived from, in blue here, from star-forming irregular galaxies. So this is now from the H1. So it's modeling the H1 of the star-forming dwarf galaxies, and we get they are sitting pretty well up here on the extrapolated relation from abundance matching. And then we also have from GEANS modeling of Milky Way satellites are sitting here as well. And this is Eridanus 2, in fact, down here. Okay, so without any feedback, we are overproducing. Or we are overestimating the stellar masses as we expect. And then once we add in our feedback, we have the standard physics one here, and the radiative feedback lowers the stellar mass by a factor of 10 in this case. However, it's still within the uncertainties, right? And still within the theoretical uncertainty predictions, let's say, by abundance matching. So, so even if it's a dramatic difference, it's hard to say how important it is in general for capturing the general properties of these ultraphanes. And I will get back to that in one slide here. Just briefly, comparing it to the literature, again, now we compare pretty well to the literature. I think we are coming into a regime here where we're sitting between these abundance matching relations. What's peculiar for us is that we never managed to get much below 10 to 4 solar masses at this halo mass. Maybe we need a different assembly history. Boosting feedback does not do this for us, okay? So even if we boost it by a factor of 100, we can still not go down to the values perhaps suggested by some of these authors here, okay? That's something that's puzzling us. How to get these extremely low galaxy formation efficiencies is something we're still trying to understand. Okay, so then we look at the I mentioned before that the molecular hydrogen may be an extremely important key aspect of understanding ultraphanes. And quite to our surprise, we did not really see this. So this is now the mass. We have the dark matter halo mass, the buildup of stellar mass in the no feedback case, and this is the standard physics one I just mentioned before. When you're in molecular hydrogen physics here, what tends to happen is that you sort of delay galaxy formation. But it turns out that we always end up with roughly the same stellar mass within sort of a few tenths of percent, 50%. So what happens here is that we form stars at much higher densities. So you need to get very dense in order to self-shield, in order to produce enough molecular hydrogen to form stars. But that's always happens. It's more or less like a delay in our case. So you end up forming stars anyway in slightly denser clumps. Okay? And to capture this, of course, I mean, this is probably very resolution dependent, so we don't know the convergence of this yet, right? But you need to get to very, very high densities, which also happens in these systems. So again, the effect is not very large, but I urge you to listen carefully also to Farah's talk later in the afternoon, where she gives us a different view on this for a much greater, larger population, where they see a big difference in terms of when you include molecular hydrogen-based star formation. Okay, now we come to structural properties. This was the hope, right? We want to see, like, can we actually see a huge difference in structural properties and therefore rule out galaxy formation models? Well, this is now velocity dispersions and sizes, okay? And our entire suite is sort of plotted here. It's all within the uncertainties of the observations, and it all clusters pretty well around some value here of a few hundred parsecs and 6-7 kilometers per second. So there's no impact of underlying physics unless your mass-to-light ratio is closer to 1, right? Which is the case for the no feedback run. So basically, this just means that the dark matter halo is setting the structural properties. Maybe not surprising. Here we unpack this a little bit. So we have velocity dispersions, magnitudes, sizes, magnitudes, and mass-to-light ratios and magnitudes. And all our simulations, regardless of how we sort of turn the physics to a different mode, will always match somehow roughly the observed population, right, within the scatter. So even if you change the masses of the galaxies by many decks, it will still lie sort of within the observed data. So I guess it's more like a warning than for simulators like myself, that matching this is not a big success of your model, right? I mean, you have to really mess up your model to not match the ultra-faint dwarf galaxy scaling relations. Okay. However, what we find is that stellar metallicities is likely a more sensitive probe to the underlying physics. This actually probes the baryon cycle and outflow physics of the systems. Here is now some data that we took from McConaughey and Kirby, and the review by Josh Simon, 2019. So we are digging into the ultra-faint iron over hydrogen abundance ratios here, so the metallicities. And it appears, at least so far in the observation, that there is like a floor here. Okay? If that's from POP3 star formation, or if it's just from star formation physics, we don't know yet. If we then plot a bunch of our simulations, so don't pay attention too much maybe to the details of this, but we follow a relation like this. And what this essentially is that we have a line of feedback strength here. Okay? So if we have a very weak feedback, we will actually overshoot this relation here. And as we go to some sort of fiducial mode where we put in the stellar feedback budget that we love and believe, we are sort of matching the observations in this way. And it's only if we actually start going beyond these models, right? When we start to have 10 or 100 times the supernova energy, where we actually underpredict the observed metallicities. It could also be that we are still missing a population of dwarf galaxies in observations here. We don't know, but at least this relation does not evolve along the observations. It's not orthogonal either, but it's a way to say we think, or a way to sort of calibrate the model more or less. If we compare this to the recent simulation efforts, we have something like this. Here's Revas and Jablonka, Corral Wheeler's work, Escala, and Andrea Macho's work in the past year or two. And again, there is this is generally a fairly good agreement, okay, with if we actually do bring the observations over here for groups. But there is a puzzling behavior where some of the groups with the very strongest feedback, they seem to generate almost metal-free or extremely metal-poor dwarf galaxies that have not yet been observed yet. Or it could also indicate that the simulations are wrong, of course. So yeah, this is this is the strongest indicator or strongest arbiter of the physics of the SM in these systems we found yet. So now in my last few minutes, let me go to step 2 where we Galactic Engineering and the diversity of ultra-faints. So now we have a suite of parameter space for understanding how the ISM and feedback and star formation physics work. So now we use a technique called genetically modified initial conditions, developed by Andrew Ponson, Nina Roth, and Martin Ray, and collaborators at UCL. So this allows you to essentially take the same initial condition and you change the initial perturbation field such that you get the same halo mass at the very end, but you're changing the formation times, for example. So you can do these changes. You can also change the mass ratios of mergers and such things. Okay? So it allows you for a very controlled way of doing galaxy formation in a cosmological setting. Yeah. So this is what we did, what Martin now did. And so we have we have a reference model and an early forming and a late forming, and one we call ex situ forming. Yeah? And they're all within the sort of confidence intervals of what we get for in a large population of halo mass growth. Okay. So what happens then? Scatter in M star M200. So here we have the stellar mass. This is the halo mass, and for exactly the same halo mass at the very end, we are finding an entire one-deck scatter simply because from the formation time. Okay. So it really matters when you spend time accreting and gas and forming stars. And reionization quenches these things at roughly the same time, redshift 4 to 5. Okay. And, but the stellar mass reached at that point is very different. Okay. So here we have the quenching epochs for these different systems, and you can see, for example, this late one that's forming late has only a few thousand solar masses in stellar mass, and it builds its mass in a very different way compared to these other ones. Okay. It's a merger-dominated buildup by dry mergers. Okay. So even though it reaches one dex here, it's when it stopped forming in situ stars, it was many decks away in terms of stellar mass. So we get this spread here simply from, this is the physical scatter from assembly time, we believe. And if we then also fold in uncertainties in the ISM model, we can get another few decks of spread. So this is the worry. My last slide is here. Okay, this has a fascinating impact on galaxy sizes. So the more dry the assembly is, the more diffuse the galaxy we get. So late time heating and deposition of stars in galaxy outskirts is doing this. So the last result I'm showing here is this, basically. So the observations are sitting here, and these points here are the simulations. And the later we assemble the galaxy, the more diffuse it is. And this, we actually now can predict a channel for diffuse ultrafaint formation. So because of this dry merging, it's a very puffy system, and it's sitting in the same parameter space as very recent diffuse ultrafaint candidates, like the one found by Oma et al. 2019 using the Hyper Supreme camera down here. So this is very exciting. So I think this is a fantastic channel for generating these systems. So I'm out of time, so let me just throw up the conclusions here, and thank you for listening.
We have time for one question, or two quick questions.
Or three very quick.
Hey, so one thing you didn't get to, presumably because it's difficult, is talking about differences in environment. However, I just want to tie in two things you said towards the end. By the way, loved it. But the difference in merger history is producing different types of dwarfs. I'm wondering if you can say anything from predicting differences in merger histories that are a function of, say, distance from the main progenitor, like Milky Way,
yes,
and therefore say something about frequencies of different types of galaxies and actually predict something.
Yeah, the only thing I can say about this is that this is exactly one of the points of this project. We want to establish these sort of channels, and once you have this, you can sort of create almost paint on this sort of, simply based on the assembly history and location around, let's say, galaxies in a pure dark matter model, for example. This is one of the things we're doing.
And following up on that, just a comment about the mass metallicity relation. It's also worth noting that the simulations predict very low metallicities for the ultrafaints are not around Milky Ways, right? Those are simulations of isolated dwarfs.
That's right.
Yeah. A quick question also about your modified merger history. So you showed changes in M star versus M halo. Do you see a tighter relation if you look at correlation with Vmax of the halo, because the earlier forming halos may be more concentrated?
With the Vmax of the halos, I mean, these are all isolated as well.
But you have,
yeah,
you're
Vmax,
modifying
sure,
the halo
yes.
formation histories, right?
We haven't looked at this, sorry, but okay, yeah, it's a good point. We haven't looked at this at all.
Okay, let's thank again Oscar.
Yeah, thank you.